Good afternoon and very warm welcome to our today's webinar, MAGNASET 2.0, New Generation of Environmentally Friendly Furan Resins. Firstly, I would like to start with the introduction of our speaker for today, Dr. Nicolas Riensch. Nicolas is 30 years old. He earned his PhD in chemistry in 2021 from University of Würzburg in Germany, dealing with organic, inorganic hybrid materials. After that, he joined ASK, and we are very glad to have Nico on board in our team as R&D lab manager for Nobek products since more than 1 year now. Myself, my name is Thomas Krei. I'm technical product manager for Nobek products in Europe, and I would like to guide you through today's webinar. Now, I would like to hand over to Nico to start with the actual presentation.
Yeah, thank you, Thomas, for a kind introduction, and also welcome from my side. Thank you for taking time today. In today's webinar, I would like to take some minutes to talk about the no-bake binder concept in general and the basics of furane resins. With the basics in hand, I will continue with the introduction of the MAGNASET technology with special focus on the environmental aspects. Afterwards, I would like to talk about our freshly developed second generation of MAGNASET furane resins, more from a performance point of view. Finally, the conclusion should convince you that the MAGNASET technology is an effective and powerful tool to significantly improve sustainability and work conditions. So let's jump right in. What is the no-bake binder concept? The basic idea of this concept was the foundry's need of a dimensionally accurate binder system that did not require heat to set, to cut down on expenses and process steps, and to save money. In general, the no-bake portfolio covers a wide range of different binder systems, which have been extensively studied in the past. This includes probably the most commonly used no-bake binder systems, such as furane, phenolic urethane, or alkaline phenolics, but also phenolic and alkyl oil binder systems are well known. ASK Chemicals has a strong background in no-bake chemistry and a huge variety of products in their portfolio, such as their well-known PepSet binder system as an example for phenolic urethane systems, or Ascorane as their signature furane-based product, just to give you some names and a few examples. And what do all of these systems have in common? They are all organic systems, which means that emissions, including BTX and overall emissions, play a crucial role, and these emissions are strictly regulated by the government. Additionally, toxic raw materials such as formaldehyde, phenol, and furfuryl alcohol, which are used as building blocks, are regulated and strict threshold values are given. And this affects the classification as well as the safety data sheets. And this also plays an important role to affect transport, storage, and handling of these resins. For example, the amount of residual free formaldehyde must not exceed 0.1%. For the different resins, different curing mechanisms are known. For example, ester curing, isocyanide curing, or acid curing, which means that also a hardener as part 2 is needed. The respective binder hardener system and the corresponding organic structure of the hardener and the emission resulting thereof has also been taken into account. Furthermore, if you have a hardener which features sulfur or phosphorus, this can cause casting defects, which you have to take into consideration. Today, we will concentrate on acid curing systems, which includes the ASK product classes Ascaran and MAGNASET. In contrast to systems based on petrochemical components such as phenolic urethane or ester curing phenolic systems, furane binders are based on furfuryl alcohol, which is a readily available renewable raw material derived from agricultural waste such as corn husk or rice hulls. And due to the self-curing ability of furfuryl alcohol under acidic conditions at ambient temperature, furane binders can be described as first true no-bake binder. So let's take a closer look on the mechanism. The addition of the acid initiates the polymerization reaction, which proceeds under chain growth and cross-linking. The starting point of the polymerization reaction is between two furfuryl alcohol monomers to build up condensation product 1, which has a methylene bridge and which still features a reactive methylyl group, which you can see here in the orange box. Further condensation affords the suggested furan no-bake polymer 2. In general, furan no-bake binders purely based on furfuryl alcohol show a good performance in terms of environmental acceptability. But on the other hand, the produced sand cores and molds indicate a higher tendency to crack and break during casting and handling due to a lack of flexibility. To overcome this problem and to enhance tensile strength and mechanical flexibility, as well as the mold handling characteristics, polymers based on urea and formaldehyde are typically added. And in recent years, this technology has been referred to as new furan technologies, encompassing our Ascaran and MAGNASET technology. The reaction scheme you can see on this slide would proceed on sand when we are combining pure furfuryl alcohol with a PTSA-based hardener, for example, under acid curing. And the new furan technology, this means Ascaran and MAGNASET, describes modified furan resins, which can contain, for example, furan urea, furan phenolic, or in general mixed resins, as well as other additives and flexibilizers. So now I've mentioned MAGNASET quite often, but what exactly is the MAGNASET technology? The background of the development of this technology are some of the main challenges that foundries are currently facing. Strict environmental regulations defining emission thresholds while maintaining an excellent casting quality. And of course, skyrocketing raw material prices, as well as increasing energy prices, gas prices, and delivering expensive are also a big issue. But it is necessary to maintain the high level of performance while at the same time adjusting the resin recipes to fit the permitted threshold values. And in this context, MAGNASET enters the stage. While conventional furan resins have a free furfuryl alcohol content of typically 50 to 95%, the MAGNASET technology is a new generation of low free furfuryl alcohol furan binder systems with a performance similar to state-of-the-art furan binders. On the following slides, I will talk about environmental aspects and answer the question how MAGNASET is classified and which influence on emission is given. Furthermore, comparison between conventional furan resins and the MAGNASET technology are made, also discussing results and performance of the freshly developed second MAGNASET generation. In the end, I will briefly talk about 2 case studies. So let's start with the labeling. As briefly mentioned, conventional furan resins have a free furfuryl alcohol content of more than 40%, mostly between 50 and 95%, resulting in a signal word danger and the labeling with skull and crossbound. For MAGNASET resins, the free furfuryl alcohol content is fixed to below 40% by definition. And this reduction of the Fa content leads to a milder classification, which you can see on the right side. The signal word changes from danger to warning, and the hazard symbols are now skull and crossbone free. The basic idea is that the MAGNASET resins have an equal performance to the conventional furan resins, despite having a significantly lower free furfuryl alcohol content. And this again affects transport and handling and offers an emission reduction potential. So let's take a closer look on the hazard labeling. On this slide, you can see the classification of acute toxicity of category 4, 3, and 2, and the corresponding hazard symbols and threshold values. Category 4, which is the lowest category of toxicity, is labeled without skull and crossbone, and this is the case for all MAGNASET resins. For the classification of the toxicity, you need the acute toxicity estimate values, the ATE values, or you can relate on the LD50 values given in this example for oral, dermal, or inhalative exposure. You can find such values in chapter 11 of the safety data sheets, and those values are determined or calculated for every resin, so also for all MAGNASET resins. And these values can be used to define the FA threshold values in the mixture. In general, both LD50 and ATE values are used to categorize the resin into the toxic categories. And considering the correlation of toxic category for all exposure classes with the free FA content, you have to orientate at the lowest given value to get the mildest classification. So in this case, it's below 40%. In category 4, the hazard statements are harmful if swallowed, in contact with skin, or if inhaled. And these phrases change to the phrase, or the sentence changed to the phrase toxic when the FA concentration is above the threshold value of 40%, which you can see here. So these sentences are for category 3 resin. A non-toxic labeling would only be given if the FA concentration would be below 6.6%. Further lowering the concentration of FA would, on the other hand, have a huge impact on the reactivity. So in our MAGNASET technology, a well-balanced ratio of reduced FA content without sacrificing the performance is given. And what I forgot to mention is we are always talking about the free furfuryl alcohol content in the mixture, which is more than 40% for conventional furane resin and less than 40% for our MAGNASET resins. So in comparison to conventional furane resins, MAGNASET has a milder classification without the skull and crossbond symbol. But what about emissions? First of all, we have to think about at which steps during the whole foundry process which emissions can occur. On the one hand, we have emissions as a result of evaporation and reaction products, including alcohol, formaldehyde, as well as other volatile organic compounds, which predominantly occur during mixing, forming, and storage. They use binder, hardener, and sand. There's a difference between fresh sand and reclaimed sand, play an important role during mixing and forming. On the other hand, we have emissions as a result of pyrolysis and decomposition, which includes BTX, NOx, and SOx emissions, as well as, for example, phenol and formaldehyde, which occur during the casting, cooling, and removal of the cast. And in general, the left side relates more to the worker health and directly affects the workers which are in contact with the volatile organic compounds, while the right side also includes the emission for the environment and direct neighborhood. Another important aspect for the worker safety and emission detection is whether sufficient extraction of the emissions are given. So if the mixing and forming process is, for example, connected to an exhaust line. And in all cases, a sufficient extraction and purification unit should be used. During mixing and forming, the used binder, hardener, and sand are responsible for emission formation. Concerning our MAGNASET resins, we have a calculated, significantly reduced amount of volatile free furfuryl alcohol in comparison to conventional furane resins. If we, for example, compare a conventional furane resin having up to 85% free furfuryl alcohol with our MAGNASET resin with just below 40% of free furfuryl alcohol, we have an emission reduction potential up to 55% if we are using the same hardener and sand and use the MAGNASET as direct, so as drop-in replacement. However, this value is also depending on environmental conditions, which includes questions such as, is the molding line connected to an exhaust line, or what about the ventilation system or the change of air? Furthermore, we investigated the occurring formaldehyde emissions during mixing via photometric analysis under lab conditions, and again compared conventional furane resins with resins based on the first and the second MAGNASET generation. And what we found, to our delight, that we were able to reduce the amount of occurring formaldehyde emissions during mixing by 39% when changing from conventional furane resins to the MAGNASET Gen 1 resin. And more recent results have shown that our freshly developed second MAGNASET Generation 2 resin has the potential to even further lower the formaldehyde emissions by up to 64% in total, again in comparison to the conventional furane resin. On the previous slides, I've talked about the MAGNASET technology and the corresponding resins in general. And on the following slides, I would like to point out some differences between the first and second MAGNASET generation. The reduced Fa content, as well as the high reactivity of the first MAGNASET generation resins, cause a slightly lower storage stability as compared to conventional furane resins. And this is one topic we wanted to address and also that we wanted to improve during the development of the second MAGNASET generation. And indeed, lab application tests with our new MAGNASET Gen 2 products indicate an improved storage stability in comparison to the first MAGNASET generation. So as you can see here, the viscosity values of the second MAGNASET, second generation resin remain on a constant level. So it's the blue line, while the values of the first generation resin slowly increase during storage at ambient temperature over an elongated period of time. And on the right side, you can see a sand performance analysis under standard reaction conditions, which means we are using 1% resin and 0.4% hardener under acid curing conditions on fresh sand. So as you can see here, we have a high reactivity and a good strength development, which is comparable to standard furane resins and the first MAGNASET generation. So here you can see the bending strength after 2 hours, 4 hours, and 24 hours. And as you can see, they are on a similar level. So on the left side, you can see that we have an improved storage stability, as well as a similar performance, which we have shown on the right side. So the goal was achieved. And additionally, what I want to highlight is that the ease of adaptation of the MAGNASET technology to existing systems. So you can use the same pipe and connections, the same amount of binder and hardener, the same mixer, the same sand, and there's also high tolerance to the used reclaimed sand. This means you can use MAGNASET resins as drop-in replacement. So let's talk about our MAGNASET resins. In our portfolio, there's a series of resin with tailored properties suitable for all types of casting and customer requests, providing good molding properties and excellent casting surfaces. Today, I would like to highlight 3 types of MAGNASET resin. Our phenol-free MAGNASET Gen 2 resin has a very low free formaldehyde content, it's below 0.1%, and a medium to high reactivity, which makes it an all-rounder for all types of casting. Furthermore, we are offering a cost-efficient mixed resin with a free phenol content below 1%, and also a free formaldehyde content below 0.1%, with a performance similar to phenol-free resins. Last but not least, we have also developed a steel variation featuring a low water and nitrogen content. And as you can see on the left, in all cases, good strength development is obtained with high bending strength after 2 hours, blue, 4 hours in orange, and 24 hours in gray. So 2 slides ago, I mentioned the ease of adaptation and a high tolerance towards reclaimed sand. And on this slide, you can see a comparison of the reactivity on the left side and sand performance and strength development on the right side on fresh sand in comparison to reclaimed sand. And when we are using reclaimed sand, the reactivity of a selected MAGNASET Gen 2 resin example is faster as compared to fresh sand, which you can see here. It's 13 minutes versus 6 and 62 minutes versus 30. And this is expected due to lower pH value and in general a more acidic sand in general. The bending strength after 4 hours and 24 hours are lower, but still on a high level for reclaimed sand. And to achieve higher strengths or fine-tune the performance, a good strategy is to add fresh sand in a certain amount, maybe 5 to 10% to the reclaimed sand, or even higher, depending on your requirements. The MAGNASET resins indicate a good compatibility with different hardeners, and the reactivity can be easily adjusted and tailored by the respective catalyst choice. So on this slide, you can see ultrasonic irradiation measurements of MAGNASET Gen 2 resins in combination with different hardeners on fresh sand. The ultrasonic irradiation method is a method to determine the work and strip time of direction systems and gives you the reactivity graphically in direct comparison. For the measurements, you combine sand, resin, and hardener in the blue block, which you can see here, which is connected to a transmitter and receiver. An impulse is generated, and the time for the impulse to traverse or to travel through the sand binder hardener mixture is measured. With increasing level of curing, the ultrasonic velocity increases. So the stronger the increase of the slope at the beginning, the faster is the reaction system, which can be related to the work time. This means that the red line corresponds to the most reactive, and the brown line corresponds to the slowest system. And as you can see, the MAGNASET Gen 2 resins can be used with all types of different hardeners, enabling to fine-tune the desired reactivity. And another benefit of the high reactivity is that sulfur-reduced hardeners of the hardener RS series can be used, which lead to lower overall emissions by reduction of the SOx emissions, and also to higher casting quality by avoiding casting defects. The determination of work and strip times give you more concrete evidence for the reactivity. So on the previous slide, I've talked about that the reactivity can be easily adjusted by the use of respective hardener. And on this slide, you can see the reactivity of a selected binder-hardener combination or system by means of work and strip time for a mixture comprised of reclaimed sand. So we have a lower pH value, loss of ignition of 3.4% with standard parameters of 1% binder of a MAGNASET Gen 2 resin and 0.4% hardener at 20 degrees with a relative humidity of 40%. And as you can see, we were able to tailor the reactivity from fast to standard over medium to slow, and we can also use sulfur reduced hardeners in different reactivity types, so more standard or a reduced sulfur system in slow, so in which the strip times amounts up to 182 minutes. And in comparison, our fastest binder hardener system has a work time of 3 minutes and a strip time of 22 minutes, which can be potentially used for serial production, while elongated work and strip times also give rise to potential applications for larger size castings. Before the summary and conclusion, I would like to talk about 2 case studies of foundries using our new resins and talk about different motivations for their decision. So the first case study is about an aluminum foundry which used an ascorane resin with a free Fa content of more than 75%. The focus and motivation is on sustainability and worker health. So they basically wanted to use the greenest furane resin available in our portfolio. And what I've shown you and what I've talked about on previous slides is that by changing from conventional furane resins to MAGNASET resins, you have the potential reduction of FA emissions, which directly affects the workers working with your molds. So by switching to MAGNASET Gen 2 resins, you should generate a high acceptance of your work stuff. And back to the example, after switching the resins, they obtained a similar performance, affording a high casting quality for complex molds in small to medium casting sizes. The second case study is for a steel foundry located in Switzerland. And the focus and motivation was on a milder classification of the resin, although sustainability and worker health play an important role as well. Since a local decree only allowed a very limited storage capacity for conventional furane resins on the cord and at the foundry. So of course, if you want to have a higher production throughput, or if you want to produce more, this is not suitable. And by using our MAGNASET Gen 2 resins, they were allowed to store up to 20 tons of the product. And also the benefit is the labeling without skull and crossbone. And in their case, for steel applications, we designed a resin featuring a low water and low nitrogen content, which they use for small casting sizes and for the production of pumps. Okay, let's sum up and make the point. I hope I was able to convince you that the MAGNASET technology is a really interesting system from an environmental point of view. The MAGNASET technology combines the advantages of a milder classification without the skull and crossbone with reduced furfuryl alcohol and formaldehyde emissions. Furthermore, due to the high reactivity and flexibility of the system, the Hardener RS series can be used to lower overall emissions. Both the first and second MAGNASET generation have a performance similar to conventional furane resins. And the freshly developed second generation additionally indicate a lower viscosity as well as an enhanced storage stability in comparison to both conventional and the first MAGNASET generation. Last but not least, I want to highlight the ease of adaptation according to the motto plug and play, as well as the good sand reclamation ability, which makes the MAGNASET resins really interesting from an economic, also from an economic point of view.